Hello, I am Lin Jiuzhou, the first author of this paper. I will present our work on perceptual similarity for measuring decision-making style and policy diversity in games, which discuss how to measure the similarity of decision-making, and we refer to as playstyle similarity. If you don't have time, let's have a brief introduction of this paper here. The problem of this research is focused on how to define and measure the style of decision-making, or refer to play style. For example, in playing a video game, I may want to play with my strategy, and others may want to play other strategies. Then this strategy can demonstrate different play styles. One solution to measure play style is directly comparing the distance of action distributions from two playing resources. But how to model in the policy or identify the case they are comparable? One previous work, playstyle distance, proposed first converting observations to discrete states and find intersection samples, and calculating the policy distance over these intersection samples. Let's the first unsupervised end-to-end playstyle measure, and we try to improve this measure in this paper. We propose three enhancements, including using multi-scale analysis to leverage states with different granularity. Next, we discuss the relation of distance and similarity from psychology to human cognition. Finally, we incorporate the idea of intersection over union in collection comparison to further improve the efficiency of discrete playstyle measures. We use several game platforms to test our measures, including some racing video games, Atari games, Game 2048, and the board game Go. We can achieve over 19% playstyle identification accuracy in all these games. In the following, I will try to introduce the paper in details. If you are busy or already know what you want to know, you can skip the later part. Okay, this is the paper information. Our paper has been accepted for publication in the TMLR. It's a long submission from August 2024. The authors of this work include myself and my two advisors, Qiuwei Chen and Wuyi Chen, in National Yangming Jiaotong University. It is called NCTU before in Taiwan. Today's storyline starts from discussing what playstyle is and its applications. Then we will introduce available methods for playstyle measurement. Next, we will delve into our methods that provide new insights for improving playstyle distance, the end-to-end unsupervised playstyle measure. Then we will conduct our experiments across several games to evaluate our new measures. Additionally, we will introduce an application of our measure for defining the diversity of the reinforcing agents. Finally, we will conclude with our findings. Now, let's start our story. So, what exactly playstyle is, and why should we study it? Furthermore, what applications are related to playstyle? Let me give an introduction. Playstyle is the decision-making style, particularly in games. It represents different preferences in decision-making, such as unique strategies or characteristics displayed by players. In human behaviors, topics like diversity, individuality, and creativity are very close to playstyle. These are inherently related to distinguishing different decision styles. With this concept of playstyle, you may already come up with that it is important to decision-making problems. There are two major objectives in decision-making style, or general decision-making, including achieving optimal performance, aka exploitation, And we have witnessed several successful results with deep reinforcement learning these days. Another objective is about the pursuit of diversity, or referred to exploration. Although we may usually say improving diversity to improve agent strength and efficiency, or generalize agent across several tasks. But how we quantify this diversity? Looking at a better game score, or tracking the state distribution from TSNE? It's possible, but it's not simple to directly quantify the actual diversity since we have to define the diversity first. And it is especially hard in environments without built-in features. But don't worry, we will discuss the solution later. If we know how to define and measure play style, we can improve many applications, such as player modeling or analysis. We can measure the diversity of decision making for both human players and AI agents. Based on this measurement, human-like AI behaviors can now be more tangible. We can collect human records and check agent similarity to these records. Additionally, there are many other possible applications like understanding player preference or verifying identity. Now, let's take a closer look at the measures for playstyle measurement. There are several approaches, from heuristic rules and game features to supervised learning, unsupervised clustering, and contrastive learning. However, our focus is on a method known as playstyle distance, since it is the first unsupervised end-to-end measure with a clear meaning definition. First, heuristic rules and game features are the common methods like kill counts, damage in shooting games. What can it provide? Anything you want. What's the performance? Most precision for dedicated case study. Then, how to get it? It is usually expensive since we have to manually engineer for each case and it is domain specific. If there are many styles or the style is unclear, then this kind of method may be hard to implement. To use these heuristics, machine learning can help. Supervised learning is a solution to classify playstyles, but it requires predefined labels. It may not handle styles not present in the training set. Another way, data mining technique like unsupervised clustering may help identify some interesting or different styles without explicit style labels. But the semantic meaning of this resource may be not clear. Taking a racing game as for example, it's common that different racing tracks have different backgrounds, like sea, forest, or city. But is that really related to driving styles? Maybe not. But this unsupervised measure may focus on these factors. Another way, using contrastive learning, like behavior style matching. This idea that we can just identify cell group and other groups rather than clear playstyle labels. Thus, it's more general to supervised learning, but it still needs to record style identity, and not clear to the case that one player may perform several play styles, or different plays, or many different players may perform the same play styles. For a more defined and reasonable approach, we can look at the similarity of action distributions. It's common in reinforcement learning to calculate the entropy of policy divergence if we have a parametric policy. But how if we do not have the policy, like the case in analyze human players? or even how to guarantee a state is comparable to two policies. The policy may be not defined or not well trained for some states. To address this problem, discrete place-style distance is a solution. We can use discrete rotations to identify some observations that's very similar in raw observation, and the gameplay policy is very similar. And we find some intersection of these very similar observations to assign as a comparable case. The action samples on these states are more comparable, and we can define the playstyle over action distributions. But this kind of method requires a decent discrete state encoder to have a good accuracy. Okay, so in playstyle distance, there is a hierarchical state discretization, HSD, to get a flexible discrete encoder. It's a hierarchical variant of VQVAE, the popular discrete rotation with neural networks. See the map? There are two gameplay results, including observations and the corresponding actions. For example, the observations in A are discretized to discrete states, and also the observations from B is also discretized to several discrete states. We can check the intersection states from this two-state set and calculate the expected action distribution distance over these intersection states, and that is playstyle distance. To have a more formal definition, we have a playstyle dataset Ni, sample from style I, including many observations and action pairs. Also, a predefined, pre-trained, discrete state encoder phi. Training this encoder do not need the playstyle label, just use observations and correspondence, and is sufficient to learn how to the game state look like. And the training data from in this paper only use only one style and is sufficient to testing many styles. For each state S encode from phi, the action distribution are deduced using a sampling distribution. For comparing two action distributions, we can use W2 matrix, where is the effort distance defined on CDF, then moving one probability distribution to another. The playstyle distance is defined as the average of expected action distribution distance over intersection states. Now, let me introduce the new insights to improve this playstyle distance. The first part is about using multi-scale states. Playstyle distance needs a proper discrete state space. If the state space is too large, we cannot get intersection states. If too small, we will lose some important information to separate not comparable states. Furthermore, some ambiguous states may need collecting several action samples to get a precise action distribution, which requiring at least T samples on a state from two comparing datasets. That means that too few samples cannot give a good quality action distribution. So, how to select the discrete state space? Let's think about how humans do. Humans also do case-by-case assessments. Then, what's the state of human? Human cognition perceives similarity on a convergence of multiple attributes, leading to a holistic understanding. That is, an observation sample has many attributes or states from a broad view to intricate details. Then, why not we use all available space we have we change the discrete state function phi into a mapping, big phi. It is an ensemble of mapping functions, very straightforward, and can get this mapping from either training several encoder or the HSD encoder has the ability to getting several mapping functions inherently. Then we can reinterpret place-style distance in a very simple way, just the uniform average of distance from different state space. Our experience show that when using multi-scale states, we do not have to care about the sample threshold T. This is because it can dilute the impact of outlier during distance computation and leverage more useful details. Thus, the trade-off between small or large state space is alleviated. Let's have an example. Preview on the racing game tours. There are 25 reference playstyles, and we have to classify the source style of a given query dataset. If the discrete state space is 1, taking every observation as a sum, the accuracy is bad. If we use the space 2 to the power of 20, as suggested by the original paper, playstyle decent, then we can have a decent accuracy, especially with the sample threshold count 2. If we further use a very large state space, it's not reasonable to have a sample rate threshold with few intersection samples. Combining all these 3 state spaces, we found that it has the best accuracy and even no clear difference with threshold 1 or 2. So just use all state space. Now we finish the first enhancement, multi-scale states. The second enhancement is about the perception of similarity. Although it is common to use a negative distance to describe similarity, we argue that it does not meet the intuition of human. For example, there is a point T. There are many points have the same distance to T. As the distance grows, the candidate circle also increases. This is about the degree of similarity. As distance grows, the distinction becomes bigger. The phenomenon was found in humans about magnitude effect, which humans diminish sensitivity to large numbers, in line with Weber-Fechner law in psychophysics, where the relationship between stimuli and perception is log-linear. As the magnitude of stimuli increases, sensitivity diminishes. Thus, we propose to incorporate the idea of higher sensitivity to smaller distance into place-style measurement. Also, we want to use probability to describe similarity like humans usually do. In the main paper and appendix, we use the property of probability and Weber-Fechner law to derive a perceptual kernel function that maps distance similarity to probabilistic similarity. And it is the exponential kernel. If you are interested in this derivation, please check our appendix A1. This perceptual kernel can be found in several places. For example, in the radial basis function RBF, and also in transformation between bacteria distance and coefficient. Bacteria coefficient is a similarity measure between two probability distributions, P and Q, and it is related to the overlapping region between these two distributions. Place-style distance suggests using W2 distance of action distribution and it can be explained as the effort, even physical or mental, to change their action distribution distance. This is from a player role. In another aspect, bacterial coefficient can be explained as an observer role, where an observer only cares about the occurrence of action outcome, and nothing how about why is the action distribution to change. Incorporating the perspective kernel into multi-scale playstyle distance. We first change the distance averaging process from the expected version to a uniform version. This change not only streamlines calculations, but also underscores the significance of encoded granularity. If two observations are very similar, they should have intersections on several state space. If not so similar, they will only have intersection on some small state space, or even no state space. Besides, to meet our probability framework, the action distribution distance has to be rescaled with a constant to ensure the expected distance converges to 1 before perception kernel. If you want to use bacterial coefficient directly, then you can skip the scaling part. This is the second enhancement, perception of similarity, that changes a distance value to probability to meet the intuition of human about similarity. Imagine that you say, oh, people A look like people B, and their distance is 0.5. Oh, there's no idea about the similarity directly. What's the distance? What's the meaning? It's not clear. But if you say, okay, people A look like people B, about 18% similarity, okay, this is clear, more clear. Then you can imagine some pattern, how they can be similar. Finally, we have the third enhancement of discrete playstyle measure. In playstyle distance, we only consider intersection of states for comparable cases. But what if intersection samples are limited or even with small intersection proportion? It may be unstable or inefficient sample for measuring the actual playstyles. So, a small intersection could indicate two scenarios. One, just distinct state visiting distribution, and it just signifies different playstyles. Two, some uncontrollable factors external to the playstyle happened, such as the environmental randomness or decisions from other players. And thus, we need more sample to have accurate prediction. So we can consider the ratio of observed sample and the actual intersection samples, a prudent approach to improve efficiency, aka using these samples to have a good precision. We can consider the proportion of intersection samples relative to the total observed samples, and it is Jaccard index, or so-called intersection over unit. It is the prevalent similarity measure in collection comparison. This called intersection over union ratio can serve as an effective playstyle measure under some specific condition, where the gain observation clearly delineate playstyle distinctions. However, it theoretically fails in some cases, like state recur due to game rules or even every state is visited. It's impractical to measure playstyle solely from observations in that case. Despite its potential limitations, our empirical result finding that it suggests that the Jaccard index serves as a handy measure when the state space is large and the randomness in the game is low. Also, the measure is simple as the equation here, just the intersection over union. Combining these three enhancements, we have a comprehensive playstyle measure and called playstyle similarity. Thanks to the uniform average of states, playstyle similarity can be understood as playstyle Jaccard index multiplied playstyle intersection similarity. Jaccard index assigns a uniform weight of 1 to each intersection state, regardless the similarity between the action distributions. And playstyle similarity infuses a probability-based weighting that alleviates the potential limitation of Jaccard index. Also, we have some good property, like a consistent interpretation of the zero values. Besides, the original playstyle distance cannot directly incorporate with the Jaccard index due to its nature as a negative similarity measure. We can have an overview of playstyle similarity. Start from playstyle distance with first introducing multi-scale states and second, the perceptron kernel to emulate human combination. Finally, intersection over union operation further leverage the overview of all observed samples. Let's playstyle similarity, a new end-to-end playstyle metric, unsupervised metric. For the experiment, we have many results to support and analyze our result, our measure. But here, we only check some result. For more detail, please directly check the main paper or even the appendix. We conduct the evaluation on various game platforms and several player types, including 2 racing games, 7 Atari games, the puzzle game 2048, and the board game Go. For player types, we have role-based AI, Protoss, human players, and deep reinforcement agents. Also, including continuous action space and also discrete action space. Our dataset and discrete encoder follows the previous work with their my official release. We also plan to release our code of this paper. In our video game experience, we will have 3 levels of discrete state space, from the most small state space, 1 to a very large state space. We use different similarity measures to perform the zero-shot playstyle classification. For example, there are 4 playstyles. We random subsample a dataset from a specific style, including many observation action pairs, as a reference dataset. Then we have a dataset sampled from an unknown playstyle and try to use a similarity measure to identify its style with the most high similarity and count the average case accuracy. We focus on the evaluation on video games in this presentation and check the performance of our 3 enhancements. First, for multi-scale state space, we already know it is effective on the racing game Taurus. In another racing game, RGSK, that is an Unity racing game, some play styles are very related to the keyboard actions, like drift or natural acceleration, and it can be captured even with the most small state space, 1. For Atari game, the 2 to the power of 20 state space is good enough, as the baseline paper proposed. We can see that in different cases, we need a proper discrete state space setting to achieve the best accuracy. But what state space is the best is a question before evaluation. Using our multi-scale state space without a sample threshold is a handy and general solution to get the best accuracy. Just use all. Next, we want to know whether the probability similarity can have the same or even better accuracy to negative distance similarity to meet the human intuition. The result in tools with continuous action space is clear that new method is better. For another racing game with discrete actions, it's not very clear, but it is still some accuracy improvement. This result verifies that probability similarity is a good alternative to negative distance similarity. Oh, forgot to say that the x-axis is about the size of a data set. Think about that. For playing results, we sample only 2 observation action pairs, or 64 observation action pairs, or even more with around 1,000 observation action pairs. The more samples should have the better accuracy. All of these cases, we can achieve over 19% accuracy. Okay, finally, we combine all of our enhancements, including multi-scale state space, procedure kernel, and the Jaccard index to compare all discrete playstyle measures. Notice that we also upgrade the playstyle distance to the multi-scale version. The purple and brown curve are good on tools and RGSK. Also, using Jaccard index only, the red line still suggests it's the decent measure, better than original playstyle distance. In Atari games, we have individual results for each game in the appendix. Here, we're combining all games to a single scenario, Atari console. Since all games on Atari platform can share the same acceleration and action scheme, thus merging all games to one game is possible. Just like we only play the Atari console with different game content, let's just play one game. Therefore, we will have 1 plus 14 discrete state encoder, including a single state space mapping, and 2-level discrete encoder from 7 games. The result still reports playstyle similarity and its bacterial coefficient variant are the best. Now, we already know that our new playstyle similarity is the best discrete playstyle measure. Also, it is more general to any supervised or contrastive methods, since they require some playstyle identifications for training. In the case without playstyle identification in the training data, like our experience, those methods are just like a random guess, since the training data is not valid. Then, is there any unsupervised and end-to-end method in playstyle measuring? Then, just discrete playstyle measures. We know that playstyle in generative models is a popular topic. We may find some baselines from that. In generative styles, the measures are usually based on a well-trained image necklarization model, inception. The basic inception score is not proper to playstyle, since it detects how an image looks like real. But in playstyle, all observations are derived from game environment and all observations are real. Another popular measure, facet inception distance, FID, is a valid measure and also common in generative styles. Its idea is based on checking the distance on the latent feature of images. Then, let's using the continuous latent feature to get the latent distance in our games. Since playstyle Jaccard index can serve as a decent measure, then we use latent features should have sufficient information to these playstyles. We can compare the main vector of the observations with either Euclidean distance L2 distance, or cosine similarity. Let's see. In torus, it's just like random, since the oscillations are very similar in background and cannot be clearly separate on latent space. In contrast, a GSK and Atari console can have better accuracy. The play-style similarity is still better, since our measure, discrete style measure, is based on the action distribution and not the oscillation solely. If we check more details on each Atari game, we found that latent similarity is only better than play-style distance with multi-scale space on two games. This result suggests that if you want to use latent similarity for playstyle, it's dangerous, since we do not know what style it will capture. In contrast, discrete playstyle measures are clearly defined on action distribution and conditional on comparable states. Now we have a good playstyle measure, then we can define the diversity of agents in de-reinforcement learning. How to quantify the diversity of the player policy? The idea is very simple. If we have a trajectory that's not similar enough to any other trajectory, then we can count it one. We can assign a probability similarity threshold, like 20%, and check the similarity of a new trajectory to all previous trajectories to quantify the diversity. If you are interested in this part, we have some apparent in the paper to support this idea. Finally, we conclude this paper. This paper proposed 3 techniques to enhance discrete playstyle measure, adopting a multi-scale state space to help the selection of a proper discrete state space. Also, using processor similarity rooted in human cognition to provide explanations of similarity that meet human intuition. Also, applying the Jaccard index to observed data to improve efficiency with all observed data. This result will help us to get a more handy and precise end-to-end unsupervised playstyle measurement. Also, we can bridge the gap between distance similarity and human cognition playstyle. Besides, we have a new tool to quantify policy diversity. I prepared some Q&A here. First, how about incorporating macro-actions? Macro-action is about a sequence of actions without interruption in action decisions. So, if you want to incorporate macro-action, you can change the distance of policy to a macro-action version, like time series distance, like string distance or DTW, or maybe just a multi-dimension action space. That may also possible. Just separate different states. Another question, maybe are there more applications of playstyle than just mentioned previously? That's also one important topic in my study. If we can measure and define playstyle, then we can try to express style that follow these measures. For example, in imitation learning, we can check whether an agent is really learn the desired behaviors. In previous, we usually check the score of agent, but how the agent really learns from demonstration is not clear. Also, diversity can help us to increase exploration, since we can measure the diversity of agent policy. Then we can make agent increase this diversity. Also, in multi-agent cell play, we can explicitly maintain the agent diversity in the agent pool. And so on. I believe playstyle in general is a not well explored domain and has many research potential in the future. Okay, overall, thanks you listen. If you can give a star to our code release GitHub repo, it will be helpful to us. Thank you.